Welcome back. Welcome to the pairing-based crypto session, everyone. So I guess we can start. I see like many of you already here. So welcome to the, again, pairing-based crypto session. We have like three exciting talks on this session. The first speaker is Benoit, who's going to be telling us about non-malleable subvector commitments. Over to you.
Thanks for the introduction. So I'm going to tell you about non-malleability in vector commitments that support subvector openings, which means that the committer is able to open a larger subvector at once using a short opening. In the introduction, I will first review the notion of vector commitments and their applications. We will see that in some applications, we need the notion of non-malleability on behalf of vector commitments. In the second part of the talk, I will explain how we can define non-malleability in the context of subvector commitments and how we can achieve it using a primitive called simulation sound subvector commitment. It's a generalization of the notion of a simulation sound subvector commitments that was introduced 20 years ago. And in the last part of the talk, I will discuss three constructions of simulation sound subvector commitments based on falsifiable assumptions. Two of them are pairing based, and the last one is based on the strong RSA assumption. I will mostly focus on this one and give some intuition as to why it is secure. And then I will give a comparison with pairing based constructions. In a vector commitment, the committer is a vector of messages over some ring, and the committer can generate a short commitment to these ring elements. The commitment should be short, and in addition, it should be possible to locally open each individual vector component using a short opening. Importantly, both the size of the commitment and the opening should be at most polylog in the vector dimension. It should even be constant in the ideal case. Initially, the motivation of vector commitments with short proofs and openings was to have short proofs in zero-knowledge databases. But later on, it found applications in other contexts like verifiable data streaming, authenticated dictionaries, blockchain transactions, and many more. And in some cases, it's convenient to be able to open a large subvector using a short opening. For example, we may want to open half of those positions using a short opening, and this is what a subvector commitment can do. In a subvector commitment, the size of the opening should be at most polylog in the dimension of the vector n and in the dimension of the subvector that we open. Historically, the first construction of vector commitment was the folklore construction based on Merkle trees. It only requires a collision-resistant hash function, and it has logarithmic size proofs. In the last decade, we have seen many constructions with constant size openings under specific assumptions. And the recent years, we have also seen several extensions of vector commitments with additional functionalities or stronger security notions. For example, we have seen functional commitments for linear functions or for circuits. We have also seen subvector commitments with short openings. They were independently considered by Lai and Malavolta and by Bonnet, Bulls, and Fish. And in terms of security, non-malleability was considered as a security notion for vector commitments by Rotem and Segev. In TCC 21, there was a paper by Rotem and Segev who showed that in some applications, actually we need a notion of non-malleability on behalf of vector commitments. Informally, it means that if the adversary is given an honestly generated commitments and local openings, then the adversary should not be able to come up with a commitment of its own and local openings that are meaningfully related to the local openings of the honest commitment. Actually, this notion makes sense in at least two applications. One of them is blockchain transactions. In this case, vector commitments commits to the internal set of a smart contract, and the local openings are verified by transaction validators. And then if the commitment is malleable, then the blockchain transaction may be malleable as well, which is annoying. Another application is in multi-round auctions. in this kind of auction, the bidders can bid for many items at once in a given round. And if an item is not sold at some round, the adversary can use the malleability of the commitment to overbid in the next round, which is also annoying. For this kind of applications, Rotem and Segev formalized the notion of non-malleability, and they showed how to satisfy this notion of non-malleability by composing a tag-based equivocable commitment and standard vector commitment. So if you want to commit to a vector of dimension n, the first step is to commit to each individual vector component using the tag-based equivocable vector commitment. And then you can commit to the resulting commitments using the vector commitment. And then you can assign the resulting vector commitments using a one-time signature secret key for which the tag is the one-time verification key. This construction is simple, but it does not extend to the subvector commitment setting, because even if the outer vector commitment supports subvector openings, if you want to open a large subvector, then you have to reveal the internal randomness of the tag-based equivocable commitments, and then you lose the constant size of the openings. In the paper of Rotem and Segev, they left explicitly open the question of constructing non-malleable subvector commitments, and this is the problem that we look at in this paper. We consider an extension of their definition to the subvector commitment setting. We show to satisfy it using a primitive called simulation sound subvector commitment, which is an extension of simulation sound trapdoor commitments that were introduced by Gary et al. In 2003. In the paper, we then give three constructions of simulation sound subvector commitments under different assumptions. One of them is the bilinear Diffie-Hellman assumption. And in this case, we need a quadratic size common reference string in the dimension of the vectors. On the other hand, we need a linear number of exponentiations to commit. We give a different construction based on the strong RSA assumption. In this case, we have a constant size CRS, but quasi-linear number of exponentiations to commit and to open. And in the last construction, we use the strong bilinear Diffie-Hellman assumption. In this case, we have a linear size CRS and a linear number of exponentiations to commit, and a quasi-linear number of field operations. So we have different constructions under different assumptions and with different efficiency trade-offs. Before explaining how these constructions work, let me first explain how to define non-malleability in the context of subvector commitments. We have a real experiment and an ideal experiment. In the real experiment, the experiment first chooses a common reference string. It samples a vector of messages m from a distribution D. It commits to it. The adversary is given both the common reference string and the commitment. Then the adversary chooses a collection of subsets Si. It obtains the subvectors of M indexed by the subsets Si. It also obtains the subvector openings for these subsets. And then in the next step, the adversary outputs a commitment of its own, vcom hat, and a collection of subsets, Ji. These are the subsets for which the adversary plans to open vcom hats in the final stage. But before doing this, the adversary is given all the local openings of M that it has not received so far. The adversary is given all the remaining local openings of M. And only then the adversary outputs subvector openings for vcom hat. The output of the experiment is defined to consist of the vector M that was honestly chosen, the subvectors M hat for which the adversary opens vcom hat, and the description of all the subsets. One important thing is that the adversary's subvectors are replaced by both symbols if the adversary copies the honestly generated commitment, or if one of the subvector openings of the adversary is invalid. This restriction is necessary because otherwise the definition would not be satisfiable. There is an explanation about this in the Rotem-Segev paper. So this is a real experiment, and what we want is in the ideal experiment is that there should be a simulator that can emulate the behavior of the adversary without seeing the commitments, without seeing those subvector openings. So the ideal experiment is the following. The experiment first samples a vector of messages from the distribution D. The adversary chooses a collection of subsets Si. The adversary obtains the corresponding subvectors of M. And then the adversary outputs a collection of subvectors of its choice. The output of the experiment is defined in the same way as in the real experiment. And what we want is that the output distribution of these messages is indistinguishable from the one of the real experiment. There are two important things about this definition. Is that first, the distribution D should be restricted to support efficient conditional resampling. It means that for any vector M sampled from this distribution, it should be possible to sample, and any subset S, it should be possible to efficiently sample a vector M prime that agrees with M in all the positions in S. This restriction is necessary because we are in a selective decommitment setting, and we need this to bypass impossibility results. The second thing about this definition is that it does not capture reusability in the sense of Damgard and Groth in 2003. To capture reusability, we need the adversary to be given multiple honestly generated commitments and multiple local openings for each one of those honestly generated commitments. But the good news is that we can satisfy such a stronger notion of reusability because we can't construct suitable simulation sound subvector commitments. As I mentioned, this is a subvector commitment extension of the notion of simulation sound trapdoor commitments that was introduced by Gary et al. And simplified by Mackenzie and Yang in 2004. In the syntax, there are 6 algorithms. The first 4 algorithms are the same as in the subvector commitment setting. The only difference is that the commit, open, and verify algorithms take a tag as input because each commitment is labeled with a tag. And then we have 2 other algorithms. The first one is a fake commitment algorithm. It does not commit to any specific message. It just outputs a dummy commitment that should look like a real commitment. And if you know the state information of a fake commitment and the trapdoor of the command reference string, then you can trapdoor open a fake commitment to any subvector that you like. This is what fake open does. And one important thing is that the joint distribution of a fake commitment and its fake opening should be indistinguishable from the joint distribution of a real commitment and its real openings. In terms of security, we also want a notion of simulation sound binding. It was defined by Gary et al. In 2003. The intuition is that even if the adversary is given equivocations, fake commitments for some tags, the adversary should not be able to equivocate by itself on a different tag. So formally, the experiment first chooses the command reference string and a trapdoor. The adversary is given the CRS. Then on multiple occasions, the adversary can choose a tag and obtain a fake commitment for this tag. For each one of those fake commitments, the adversary can also see equivocations. This means that the adversary can choose a subset Si, a subvector MSI, and obtain a trapdoor opening of the fake commitment for the subvector MSI. And the adversary can do this on multiple occasions for different subvectors and the same tag. So the adversary can see equivocations of any fake commitment. And yet, the adversary should not be able to equivocate by itself on a different tag. So in the final step, the adversary outputs a new tag star, a commitment vcom star, 2 subsets S1, S2, 2 subvectors MS1 and MS2, and 2 subvector openings. The adversary wins if the tag is a new tag and if the 2 subvector openings verify. And if there exists an element in the intersection of S1 and S2 such that the 2 subvectors disagree. In this case, the adversary wins. And we can prove that if we can satisfy this notion of simulation sound binding, then we can build non-malleable subvector commitments. To do this, we need to combine a simulation sound subvector commitment and a strong one-time signature. The idea is that the tag of the simulation sound subvector commitment is the verification key of the one-time signature, which is used to sign the commitment, and the signature is included in the opening. Actually, this construction is not new. It was already used to construct reusable, non-interactive, non-malleable commitments. There is a construction similar in the paper by Mackenzie and Yang from 2004. And what we show is that it also works in this setting. So in the rest of the talk, I will focus on constructing simulation sound subvector commitments. And we can do it under 3 assumptions. The first one is the bilinear Diffie-Hellman assumption in asymmetric pairings. It's a standard assumption introduced by Bonnet and Franklin in 2001. The second assumption is less standard. It's a Q-type assumption. The assumption says that for a random alpha, if you are given a bunch of powers of alpha in the exponent in both source groups, then you cannot compute a pairing of G and G hat raised to the inverse of the sum of alpha and a C of your choice. This assumption is not a standard one, but it's not a new assumption either. It was introduced 20 years ago. And the last assumption that we use is even older. It's the Song RSA assumption that was introduced by Barich and Fitzman in 1997. And I'm going to focus on the construction based on Song RSA in the last few minutes, because it's simpler to describe. The construction is based on the subvector commitment by Lai and Malavolta, which is itself inspired by the Catalano-Fiore vector commitment based on RSA. In the common reference ring, there is an RSA modulus n and an element G0, which is a generator of the subgroup of squares. The scheme also uses a sequence of public primes, but they don't have to be explicitly included in the CRS. They just need to be longer than all the committed messages. So you can just take the first n primes above to the k if you commit to k-bit messages. If you want to commit to a vector of dimension n, the first step is to compute a sequence of generators gi, where each gi is g0 raised to the product of all the primes except the ith one. For security, it should be infeasible to compute the ith root of this gi. And then, using these generators, the committer can compute a deterministic Petersen commitment in a hidden order group. Actually, it's not quite a Petersen commitment because the generators are not independent, but still the commitment is binding under the strong RSA assumption. And then the idea of Lai and Malavolta to make it, to turn this construction into a subvector commitment was that if you want to open a subset of indexes S, you can first divide the commitment by the subcommitment to the subvector that you want to open. And when you do this, what you have on the right-hand side is G0 raised to a power which is the sum of terms, and all of these terms are divisible by the product of primes indexed by the set S. And then the committer can compute a root of this thing on the left, and this root will be the subvector opening. Lai and Malavolta showed that this construction is actually binding as a subvector commitment under the strong RSA assumption. And to turn this construction into a simulation sound one, there are two difficulties. One of them is that we need to randomize the commitment because it's deterministic, and we need to make it equivocable and then randomized. To do this, we introduce an additional generator G, which is a G0 raised to the product of all the primes. And then we can compute a randomized Petersen commitment. Actually, it's not quite a Petersen commitment because the generators are not independent, and also because the discrete log of G with respect to each GI is public, but it does not affect the binding. What we need for binding is that the inverse of this thing, both phi of n, should be difficult to compute. And actually, the second difficulty that we need to solve is that we need to find a way to equivocate on the adversary tags. And actually, we do this using 3 observations. One of them is that we can equivocate without knowing the factorizations. We just need to know the ith roots of each GI. Also, we don't need to equivocate on adaptively chosen tags. The tags just have to be chosen by the adversary before the adversary obtains the commitment key. It's a weaker notion of simulation sound binding, but it's sufficient for non-malleability. And the last observation is that the primes don't have to be fixed. They can be derived from a hash function applied to the tag. We just need a hash function that outputs prime numbers exactly in the general Alevi-Rabin signature scheme. And actually, the same idea was used in the construction of non-malleable commitments by Gennaro in 2004. So the construction that we give is identical to Lai-Malavolta with the difference that the commitment is probabilistic. And the other difference is that for each tag, we choose a different set of prime numbers and a different set of generators. And actually, if we do it if we commit in the naive way, we need a quadratic number of exponentiations. But this can be reduced to n log n exponentiations if we use an algorithm of Bonnet, Bunz, and Fish from Crypto 19. In terms of security, we can prove that the construction is simulation sound binding under the strong RSA assumption, and if the hash function is collision resistant. So we can give a reduction that breaks either the strong RSA assumption or a collision or the collision resistance of H. I won't have the time to explain the proof. In the paper, we also give two constructions based on pairings. One of them is an adaptation of the strong RSA-based constructions in the pairing setting. In this case, the number of exponentiations is only linear in n. We give a different construction based on the bilinear Diffie-Hellman assumption. It's based on the subvector commitment of Gorbunov et al. From CCS20. And we combine it with water signatures to achieve equivocation. So if we compare these constructions in terms of efficiency, the one based on strong RSA has the shortest CRS size. The CRS size is constant, but the slowest commitment time. The one based on the Q-type assumption has the smallest opening size. It's only one group element. And the one based on DDH has the fastest commitment time. It's strictly linear time, but the opening time is quadratic in the worst case, and the CRS size is quadratic too. One open question is to achieve both strictly linear size CRS and a strictly linear time to commit and to open. So to conclude, we obtained the first constructions of non-malleable subvector commitments with reusability, using as a building block simulation sound subvector commitments, which we build from falsifiable assumptions. Two open questions come up. One of them is to achieve both a strictly linear CRS size and a strictly linear time commit and open time. Another open question is to achieve post-quantum security. And the last one is to have a transparent setup, because in all these constructions, we need a trusted setup. And this is it. I'm a bit out of time.
Thank you. Questions? Yeah.
Thanks for the talk. So for post-quantum instructions, do you mean efficient or like just any proof of concept, like asymptotically optimal?
You mean
like say if I use any heavy object like FHE or some heavy lattice objects like batch proofs or etc. Even using those, do you think post-quantum instructions don't exist for?
No, I think it's possible to construct them, at least if you want a notion of same set binding. It's a weaker notion of binding, which means that you cannot open the subvector in two different, for the same subset. Actually, in the stronger notion, there should be an element in the intersection of the two subsets where the two subvectors disagree, which is stronger. And I'm not aware of anything like that in the post-quantum setting. I know that the paper by Wee and Wu from Asiacrypt 23 can achieve same set binding for subvector commitments. It could be used as a building block for DCS.
I see. So strong soundness, the strong notion of soundness that you define, the second one, that one is unclear. The first one probably can be done. That's what that's what you're saying?
Yes.
Thank you.
Any other questions?
Thanks. Great talk. Is there already an implementation of this?
Excuse me?
Is there an implementation of it?
No, I did not implement this.
Okay. Thanks.
So thanks for the great talk. I have a question. So the work that you're referring, this Lai Malavolta, it was translated to the lattice-based setup in the paper in Crypto 2022. And I was wondering, like, can the same techniques are still possible to translate to the lattice-based settings?
Which paper do you mean by?
There was like ACLMT22.
The SNARK paper.
Yes, but inside the SNARK paper, it's essentially turning vector commitment into SNARK.
Yes.
So the heart is the
I see what you mean. Maybe it's possible. Yes. I haven't checked, but
okay, it was just
maybe it's possible.
Thank you for the talk. My question would be, could you please comment on the practical applications, if any, of this particular type of vector commitments? I'm aware of vector commitments being used quite often in snarks and NISICs and in public infrastructure, let's say so. But in those cases, the RSA assumption would be a bit too strong. So what are you thinking in terms of applications of those?
Actually, if you want to use them in snarks, it cannot be used in snark because it's not the kind of security notion that you need for snarks. You need something like simulation extractability or things like that, but this does not imply simulation extractability. So it cannot be used for this context. It can be used for what the applications mentioned by Rotem and Segef, blockchain transactions or multi-round auctions. If you want to bid for many items at once, if you want to concisely open one of the commitments, if you want to bid for many items at some round.
I see. Okay, thank you.
Okay, let's thank Minu again. Great. So the next talk is another interesting one. It's on getting traitor tracing without trusted authority from registered functional encryption. And we have Monushij who will tell us more about it.
Okay. So good, right? It's working. Okay. Yeah, so I'm going to talk about, hello everyone, I'm going to talk about traitor tracing without trusted authority from registered functional encryption. And this is a joint work with Pedro Branco, Russell Lai, myself, Julio Malavolta, Ahmad Reza Rahimi, and Ivy, who also made part of these slides actually. So let's begin by, so this is like the quintessential scenario like that we use so frequently these days, group messaging in WhatsApp and Signal and so on, these messaging apps. So let's say there are L users in this group messaging scenario who wants to broadcast messages to each other, and we might assume that L is just 1024, assuming that like WhatsApp supports groups of size maximum 1024, right? So like group messages are very frequent these days, so we want small ciphertext sizes. Like ideally, they should not be scaling up with the size number of the participants in the group. They should be like, typically they should be secure, of course, like like the messages, like the ciphertext exchange should not be easily decryptable without any like secret key, valid secret key. And additionally, we would like to trace a user that leaks its own secret key, either intentionally or accidentally, let's say. Let's say the device gets stolen, the device gets compromised, and somehow we should be able to trace the user in that setup. This would also allow us to somehow exclude this like user from the group later. Okay, so with this setting, the very natural cryptography primitive that comes to our mind is that of traitor tracing. Traitor tracing is like the setting of traitor tracing is as follows: there is an authority which generates some public parameters or master public key, and it also generates the user secret keys. It distributes these user secret keys to individual users. Encryptor encrypts with respect to these public parameters to all these users. And for correctness, any user with a valid secret key should be able to decrypt this. For security, we typically require CPS security, but additionally, we now also require something called a trace algorithm, which basically ensures as follows: that given an attacker which shows up with a device that can actually decrypt your messages, like this trace algorithm can like access this decryption device as a black box, and it can determine at least one corrupted user from this set of users. So traitor tracing, as it turns out, it has been like the topic of a long series of works, improving efficiency with respect to ciphertext size, public parameters, secret key sizes, and so on. However, we don't really see its application in practice as such, even if it's it's a very nice primitive, I feel. So one reason for this is like our speculation is that like because of this presence of this trusted authority, what it leads to is basically a key escrow issue. So this, if the authority itself gets corrupt, then there is no security as such. Like it has a hidden trapdoor. with which it can decrypt anyone's like messages and stuff. So, so our goal in this work was to build an efficient traitor tracing, ideally without a trusted authority. So the goals is to basically remove this trusted authority and have, while still having a non-trivial concrete efficiency, where ciphertext size grows sublinear in the number of users. And we want security from like simple and well understood algebraic objects, not full-blown program obfuscation, for example, right? So with this, in this context, our contributions are as follows. We propose a new model for traitor tracing scheme without trusted authority that we name as registered traitor tracing. And this follows, like we show a transformation from the related primitive of registered functional encryption, which again got recently formalized last year. And we show that there's a generic transformation which holds from registered functional encryption to registered traitor tracing. In particular, we built a registered quadratic functional encryption schemes, that is an RFE scheme for quadratic functions in a weak setting that we will talk about in a bit, but it has a transparent setup. So that is it's a very crucial advantage. However, the proof of security we have is in the generic group model, but we show that this is enough. This is sufficient to build a registered traitor tracing in the unbounded collusion setting. Further, we also have a registered linear functional encryption that is RFE for linear functions or inner products. This we like proof is in the standard model, but from a parameterized assumption that we show to hold in the generic group model. Again, like we show that this RLFE for like is sufficient to get like registered traitor tracing in the bounded collusion setting. We have a prototype implementation for this registered quadratic functional encryption through the like registered traitor tracing through this RQFE. And finally, we have more applications for our RFEs as well in our paper. So just to like before going into the technical details, just to like discuss a bit of related works. So all prior schemes, as I said, rely on this trusted authority, except the very recent work of Luo, Luo, which requires no setup at all, but it relies on IO. The construction is based on IO. It has non-compact master public key. That is, the master public key grows with the size, with the number of users, and the decryption is randomized. Like it needs random access to this ciphertext and public key. On the other hand, our framework is inspired from registration-based encryption and like a follow-up of it, which like culminated into the model of registered FE, where the primary goal was to basically remove this trusted authority from IBE, ABE, and functional encryption. So there are some concurrent works in this scenario, one of which got accepted here only. It will be presented day after tomorrow, I guess, DPY23, which builds registered linear FE in the generic group model. They have a non-transparent like setup as well. And then there is another work which improves on the state of the art by Zhu et al. From Eurocrypt 24. This gets very selective simulation secure RQFE and RLFE from variants of the K-Lean assumption with non-transparent setup. But they like all of their constructions have non-transparent setup. So before going into the technical details, let's briefly recall what is functional encryption. So functional encryption comes with these 4 algorithms: setup, keygen, encrypt, and decrypt, where setup is basically generating a pair of master public and secret keys. Key generation generates a secret key for this function with the help of the master secret key. Encryption takes in the master public key and generates a ciphertext for a message. And decryption decrypts the ciphertext with this function secret key to reveal the function of the message. So while this is the correctness of functional encryption scheme, the security informally is as follows: given the master public key, given a bunch of secret keys queried by the adversary, maybe adaptively with respect to a challenge ciphertext, the ciphertext encrypting 2 messages mu0 and mu1 should look indistinguishable. The entire distribution should look indistinguishable as long as the functions behave the same way on these challenge messages. So while this is the security guarantee of functional encryption, we see that if the setup itself, like the trusted authority somehow gets corrupt or the master secret key even gets leaked, then there is no security guarantee anymore. So with this in mind, there were many other works, but the most recent one which was proposed to tackle this issue was that of registered functional encryption, where there is still a setup, but there is no master public key, master secret key as such, like generated by the setup algorithm. But what we have is now like the setup computes as a common reference string, CRS, preferably a transparent one. User samples, like user has its own key generation algorithm. It samples its own key pair, public key and secret key, with respect to this common reference string. And then the users need to register their public keys and the functions that of their choice to a key curator, with a key curator. So this key curator has the job of deterministically updating or aggregating these keys into a short like master public key. So they get this information of public key comma f for all these users from 1 to L, let's say, and they have the job of like aggregating these public keys into a short master public key and L helper secret keys, each of which should be short. Okay. And also crucially, like if you are updating them one by one or cumulatively, then the number of updates in the entire lifetime of the system should not grow with the number of users at any time. So they should be sublinear. Okay. So for security, informally, it is again similar to FE, but except now because the keys are now can be like keys can be generated by the users themselves, we need security against maliciously generated keys. So RFE should be able to handle that as well. Okay. So let's look at the like in a bit more detail. Let's look at the like syntax of slotted registered and functional encryption, where like we assume that the public keys are aggregated in one shot where all the public keys are already available. So here the setup assumes that there is a known bound on the number of users whose public keys will be aggregated, and that is L precisely. Setup basically outputs a CRS, and the key generation then is run by individual users with relative to the CRS with this index L. So user L self generates its public secret key pair with this index with respect to this index L. There is an aggregation algorithm which, when given the CRS as input and a public key and a function like a set of public key function pairs, it has the job to aggregate this into the system and generate a master public key, and with like sufficiently many helper secret keys. So crucially, this aggregation is a completely transparent process. It's a public deterministic process, can be run by anyone who knows these CRS and public key and functions. And whereas the master public key and each helper secret key should be short. So ideally constant sized or like sublinear in L, again, the number of users. Okay. So encryption is like as before, it takes the master public key, the aggregated master public key, and it generates this ciphertext with respect to this message mu. And for decryption, users had already generated their own secret keys. Now, addition to that, we need these helper secret keys that was computed like deterministically as output of aggregation process. So user needs like this secret key for L, helper secret key for L, and then it outputs mu prime. By correctness, we have this mu prime to be f of mu, fl of mu, the function that it registered with this key curator. Okay. So we call this a weak RFE scheme when all the functions are known at the time of setup. Okay. So these functions, the set of all functions are known at the time of setup, and they might also be given as input to the setup algorithm. So then we call this as a weak RFE scheme. We will see it why it is required for us, like why is it sufficient actually for us. So we additionally also require the ciphertext to be short in order for our application to work in our final application in registered traitor tracing, where we want the ciphertext to not grow with the number of users. Okay. So here is our construction idea. We essentially compile a traditional quadratic FE scheme to a registered version, essentially showing a way to distribute this quadratic FE scheme through some kind of master secret key homomorphism. What it says is basically that there should be a relation, an encoding relation between the master public key and master secret key of each quadratic FE instance. Okay, the base quadratic FE instance, which is this linear, relation should be linearly homomorphic. So given the two different instances of quadratic FE scheme, computing MPK0, MSK0, MPK1, MSK1, I should be able to like publicly combine them and generate a joint master public key, which is just the addition of those master secret keys. Okay. Further, we also require the key generation for this base quadratic FE scheme to satisfy some kind of linear homomorphism for a fixed function, for any function that you fix from the class of functions. So what I mean is that if you generate using those MSK0 and MSK1, if you generate two separate keys, SKF0 and SKF1, they should again be publicly recombinable, or I can club those like secret keys to form a global secret key for that function under the global quadratic FE scheme. And the star is essentially a group operation in our paper. So, yeah, so given this, now if each of these users sample a different instance of quadratic FE scheme, they have their master public key, right, put into their public keys, own public keys, and given those master public keys in their public keys, they can be aggregated easily using this public operation for L such users. They are publicly computable, as I just said, and the interpretation is that each user like shares the has an additive secret share of the global master secret key now. So because the encryption is done under this global master public key, so it should be like decryptable with respect to a secret key which is generated from the global master secret key, right? So therefore each user should also publish some kind of helper information in order to decrypt their own shares, right? For their own share and other shares as well. So what I mean by this, that each user J provides some additional helper secret keys for all the other users except itself. So it generates a function secret key for the same function for all functions Fi except its own under its own master secret, right? Once you do that, you can arrange these secret keys in a nice matrix format, which the first column of which is generated like the secret key for F1 generated with respect to slot 2 generated with respect to slot L, except the diagonal. So you don't have this diagonal element. But then the key generation, because it's a linearly homomorphic scheme, you can combine them like using this key generation to form this partial secret keys, which lacks only just one secret key that is available from the ith user now, right? So the ith user holds the ith share, so it can club that again to form the global secret key corresponding to that particular ith function, and with which it can now decrypt under the any encryption generated under the global master public key. So we essentially instantiate this template using the quadratic FE scheme of Baltico et al. From 2000 Crypto 2017, which was originally proven secure in the GGM, but it's probably the only known adaptively secure quadratic FE scheme till date. So we build a weak RQFE scheme proven in a simplified setting where the adversary provides randomness of maliciously generated keys, but we show that we can lift it up to security against malicious keys by having there are 3 methods in our paper. The first is generic based on NIZIC, which basically forms well-formedness of all these public keys. The second one is a random oracle based construction where the setup still remains transparent. And the third one is a tailor-made approach, which specifically tailor-made for our registered quadratic FE scheme, which does not rely on any hash, but it loses the transparency of the setup. So essentially, this aggregation that happens here, the validity checks that happen there on the formation of these public keys is in a kind of BLS style verification, BLS signature style verification. Okay, so we plug this framework into our compiler, which is again following which again follows from a prior work where it was shown that how to build to build full traitor tracing scheme, it is enough to build private linear broadcast encryption, which is basically broadcast encryption along with a trace encrypt algorithm. I mean, in 2016, this was shown that PLBE can be abstracted out as a quadratic functional encryption, computing a very simple function indexed with this index L, and the inputs are an index I and M, which is essentially revealing, computing a message by revealing the index, right? It outputs M if and only if I is less than or equal to L. This comparator function you can compute using a quadratic FE scheme, and because these functions are simple in structure, the main our main observation was that weak RQF is sufficient. These are known at the time of setup, so you don't need full-fledged registered quadratic FE really. We formalize this full chain of transformations in the registered setting in our paper, and these are our implementation numbers. We have for 1020, we had in mind WhatsApp to model WhatsApp groups. So the CRS size is around CRS and both public key sizes are around 100 kilobytes. Master public key and ciphertext are around 6 kilobytes. And the secret keys are helper secret keys are super short, 100 bytes and 200 bytes each. Okay, and these are our numbers. So I would really encourage for anyone interested in this work, I would really encourage to look into this, into our paper for more details. So we have some additional applications for our RFE schemes as well. As I said, like we built a registered linear functional encryption scheme, and we show that we can build a registered threshold encryption out of that thing. So what is the registered threshold encryption? It is a threshold encryption, just that we don't have a trusted authority anymore again. We have users sampling their own public secret key pairs, where the public key is aggregated into a short master public key. But now the ciphertext also grows with only this threshold key, not with the size of this full, like the number of users. And this threshold can be dynamically chosen at the time of encryption, actually. System preserves. So this notion of registered threshold encryption generalizes distributed broadcast encryption as well. So the idea is as follows: to get a T out of L threshold, like registered threshold encryption, any user I from 1 to L runs a key generation for a linear function, which is this, again, this known vector 1 I to the T minus 1. And for encryption, you sample a random T minus 1 degree polynomial, where the constant of this polynomial is the message. And you secret, you encrypt the coefficients of this polynomial as a T minus 1 dimensional vector. So for under the hood of RFE, right, RLFE. So once you decrypt it using RLFE, the inner product basically essentially enables you to learn the polynomial evaluated at point I, and given such, because it's a degree T minus 1 polynomial, given such T points, you can club them together to recover the polynomial in the exponent of a group to learn all this, to learn the message finally, right? You can reconstruct the polynomial in the exponent of a group. So we show that like this registered linear functional encryption indeed implies RTE, and with our RLFE, unfortunately doesn't have a transparent setup, but if we instantiate with our RQFE scheme, it still has a transparent setup. So summary, we have a new model for traitor tracing without a trusted authority that might be useful for actual public application, like real applications in practice. We have a concretely efficient RQFE scheme, and we show a transformation from there to registered traitor tracing with a transparent setup. We have a prototype implementation. We have more applications, for example, RTT with bounded collusion. We show that RLFE can imply RTT with bounded collusion as well as single key RFE for all circuits. And I also talked about registered threshold encryption. So there are the things are much more detailed in our paper. So please do look at our paper for more details. And thanks again for your attention. If you have any questions, please feel free to ask.
Questions?
So in order to get this RTT from RQFE, does adaptive security is necessary, or we can build from selective security?
So we get adaptively secure registered traitor tracing based on adaptively secure FE. So we wanted to have the best possible security notion for traitor tracing scheme, which is adaptive security. And the only known adaptively secure quadratic FE scheme is that of, to my knowledge at least, is from this Baltico et al.'s paper. That is proven in the generic group model. But otherwise, if you get a selectively secure quadratic FE scheme, I mean, you might get a selectively secure traitor tracing scheme as well in the registered setup. Where you corrupt all, where you need to corrupt all the users before and so on. Yeah.
So what's the ciphertext size in use?
The concrete sizes, you mean? They all
asymptotically in the.
Okay, asymptotically they all grow with root L. Like L is the number of users, let's say 1024. So around, root L, order root L. Concretely, if I recall correctly, the ciphertext size is something like 6 root L plus 4 group elements. Yes. Thank you.
Any more questions?
Thanks for the talk. So square root dependence, right? In terms of number of users with respect to the traitor tracing result.
Yeah.
Is it in all components, public key, secret key, as well as, I think public key is large, or public key is also square root of L for tracing? When you can.
Yeah, I think, yes, public keys grow with L actually. Yes.
Secret key and ciphertext are as square root of L.
Yeah, secret keys, I think helper secret keys are constant size. Master public keys, again, like square root of L. The public keys, like because of this helper information, you need to put into public
Let's
keys. They
ignore
go with it.
helper secret keys. I'm just trying to figure out the length of a receiver's key in a data tracing system, like just a decryption key, a single decryption key. Does that?
A single decryption key.
Yes.
I don't recall the exact number, but I can get back to you.
Okay.
I think it's something square root of L or even shorter.
Okay.
Yeah.
And there's nothing known from, from lattices, we know optimal data tracing. So it's like that same, you can't translate to this registered model, right?
Yeah, it's a bit difficult, I think. I mean, I don't know if there is a way to distribute. I mean, for example, quadratic FE is not known from lattices and plausibly not to be constructed from lattices. I guess, I mean, it needs newer techniques, I guess. But this framework, I am a bit doubtful if it can be applied to lattice-based setting. We need a construction from scratch, maybe, from lattices. Yeah.
Thank you.
Yeah.
Any more questions? So I had a quick question about the model. Can the users join in dynamically, like even though you've bounded it to L? Are
Yes,
they allowed to
it
join
can,
in
it can.
dynamically?
So there's this new framework of registered attribute-based encryption, which shows the power using a powers of 2 technique. You can abstract out the updation process entirely, so that users you'd only need to focus on the slotted stuff, slotted scheme, and then using 2 slotted schemes, you can show that using a powers of 2 technique, you can allow the users to join dynamically.
Okay. And the number of times you need to update remains
Is
like
short, yes.
log.
Polylog in L. That's ideally.
Okay. Any final call for questions? Okay. If not, you can catch, I guess, Monush's offline and ask. So let's thank him again. Okay, great. So we have the final talk for the session, and it is on tightly secure, non-interactive BLS multi-signatures, and Renus will tell us more about it.
Yeah, okay, hey. So today I will talk about our work on tightly secure, non-interactive BLS multi-signatures, and this is joint work with Benedict. Can I also have a pointer, like a red laser point, or doesn't that work? No, it doesn't work. Okay, so let's start with what a multi-signature is. So in a multi-signature, we have n signers, and each of the signer has a own public key and a secret key pair. And now they come together and they want to sign a message M, and in the end, they generate a signature. And then they can simply take the signature, and anyone can verify when it has the list of public keys. And for the security, we just assume unforgeability, where we assume, okay. Okay. Yeah. And so for the security, we just assume standard unforgeability, where we assume that at least one of the signers is honest. Okay, why do we care so much about multi-signatures? Probably because they are used in blockchain systems and also for consensus protocols and so on. And what do we want from a multi-signature? As usually, we want security and efficiency. So what does that mean? Concretely, oh, I guess that's the wrong slides. But yeah, so concretely what we want is small signatures, and what we also want is a non-interactive signing protocol, which means that each party just sends one message, and then they can locally compute the combined signature. And for security, what we care about is, okay, we want security from a standard assumption such as CDH or DDH. And we also want a tight security reduction. What that means is, so usually in cryptography, we prove security via reduction from the by a reduction from the security of the scheme to the hardness of some computational hardness problem. And we want that the advantage, like the ratio of the advantages and breaking the scheme and breaking the hardness assumption is a constant. And that means tight security. Okay, let's look at an example of a multi-signature scheme to understand how they work. So let's take the BLS multi-signature scheme. And so again, we have n parties here. You want to PN that want to send some message M. And each party has its own key pair, okay? And how the scheme now works is each party takes the message M, hashes it, and just computes a regular BLS signature with its key, right? And then it broadcasts that message. And then each party can just locally collect all these shares and multiply them. And that will give the full signature. And okay, we see that's a very good scheme, right? It's non-interactive, it's BLS-based, so it's very efficient, right? But the problem is that that approach is insecure. So why is it insecure? Okay, let's look at the case of two parties. Okay, so we have one honest party and one malicious party. So the honest party just it makes its public key public. And what the adversary then does, okay, it samples some R, some element in that P, and then it computes its own public key as the inverse of the honest public key multiplied with G to the R, which is just essentially a shift of the inverse of PK1. And now when we look at the signature share, okay, sigma 1 has this form still, and now sigma 2 has this form. And when we combine these signatures, we see that the combined signature is just the hash of the message to the R. And we know that the adversary sampled R, so he knows R. And what it means is forging is easy, right? And this kind of attack is called broke key attack. And okay, now there are many solutions or some solutions in the literature to prevent this kind of attack. So one of them is a COSC assumption, where you simply assume that the adversary knows the secret key. Or what you can also do, you re-randomize the public keys so that in the end, so that this combination of public keys, it does not cancel the SK1. Because when you re-randomize them, then the linear combination is unlikely to be 0. And also there was a technique from Ristenpart and Jelek from Asiacrypt 2007. And here that one is very interesting because you can simply provide a proof of knowledge, a kind of proof of knowledge of the secret key, which is computed as the hash of public key to the exponent SKI. So essentially it's like a BLS signature itself, right? Okay, and now with these solutions, we know that this scheme essentially is secure. It's non-interactive. You can prove security from CDH, which is great. However, one problem still remains. The security loss of this signature scheme, of this multi-signature scheme, is linear in the number of hash queries that the adversary can do. And this is not, I mean, there is even an impossibility result that you cannot circumvent this security loss. So what should we do? Because, I mean, BLS is efficient and so on, but we know that the security loss is inherent. So what should we do? Yeah, so the question is, can we even design a tightly secure BLS multi-signature or not? And our result is that we can do that. So what we do is first of all, we construct a tightly secure single signer BLS signature, which just outputs a normal BLS signature that you can verify with the BLS verification algorithm. And we show that, we construct that from CDH and the random oracle model. And then we can like make this single signer signature scheme into a multi-signature scheme. And this reduction, this transformation, we can do it tightly, secured, and via this technique of Rissenpath and Jelek. And we need to adapt a bit, but mostly it follows this transformation of Rissenpath and Jelek. And with that, we get a tightly secure multi-signature BLS scheme. And here you can also have a comparison table where we compare to previous non-interactive multi-signature schemes in the pairing setting. So this is our scheme, which is based on CDH and tightly secure. And here you can see the other schemes. And now you can also have a look at the, because here you can see, okay, there are two schemes that are also tightly secure multi-signatures and based on ROM and CDH. But now when we look at the concrete efficiency, okay, we see that our scheme, okay, here you can see these schemes, and see that our scheme outperforms both in computational cost and also the signature size mostly. And yeah. Okay, so since this transformation is, it mostly follows the technique of Rissenpath and Jelek, I will now try to concentrate on this scheme, like how we construct this single signer BLS signature scheme. And yeah, let me try to explain our techniques. So usually what you do for a proof in this kind of setting is, okay, we want to build a reduction, reduction to some hardness problem. Okay, what does that mean? Okay, we get a challenge X, and then we usually embed this challenge into the public key, which the adversary sees, and then you can make arbitrarily many, okay, polynomially many signing queries, and he can ask us to sign a message ME, and then we have to provide, we have to simulate a signature, right? And then in the end of the game, he just outputs a forgery, and then we somehow convert this forgery into a solution of X. And let's look at the proof specifically for the BLS signature scheme, like the previous BLS signature scheme. So how it works is, okay, we have a reduction to CDH. That means we get a pair XY, a CDH challenge. And in the end, we need to compute G to the X times Y in the exponent. So what the proof of BLS does is it takes this challenge and then it embeds the X component into the public key, right? And then it guesses the forgery message. And what it does for the hash queries, okay, for all messages that are not the forgery message, it programs the random oracle as here. So it just samples an Ri from ZP, and then it takes it to the exponent, G to the exponent of Ri, and outputs that as the hash value. However, for the forgery message, M star, what it does is it takes this epsilon component, this Y component, and it embeds it into the hash. Now, how can we simulate signatures? Okay, can just compute X to the Ri because we know this Ri, which is essentially a trapdoor that we know, right? And now for the forgery, we know, okay, that the adversary computes a BLS signature, and that directly gives a solution to CDH. Okay, but here we see that the reduction has to guess the forgery to make this work, right? Because it needs to know where to embed this CDH challenge. So how can we somehow try to prevent this security loss, which is linear in the hash, in the number of hash queries? So what we do is, our idea is the following. So instead of one key, we try to use two keys. What happens if we use two keys, right? So the signer has two keys, PK0 and PK1, also with the corresponding secret keys that it samples. And now when it needs to sign a message M, it just simply chooses one of the keys for each message, and it signs this message just regularly as a BLS signature, as what we have seen on the previous slide. So for example, when it chooses, it gets one message. And for that particular message, it chooses the first public key, like PK0. Then the signature is just BLS signature for this public key, which is hash of M to the SK0. Okay, how does that help for our security proof? Can we now get a tight security proof or not? And now the proof idea of the security reduction is the following. Again, we want to reduce to CDH. So we get a CDH challenge. And now what we do, because we have two keys, okay, we can just sample one key honestly. That means we sample a secret key honestly, and then compute the public key as that. Okay. However, for the other key, we embed this X, the CDH challenge, the X component of the CDH challenge into that key. Okay, and now for the hash queries, what do we do? Okay, for each message, we just randomly either do that simulation or that. So we either embed the CDH component into the hash, or we just we somehow program the random oracle like honestly, like by knowing the trapdoor. And we do that for each message, just randomly either use that kind of programming or that kind of programming. So essentially what we do is that we split the message space into two subsets. Like this one is, you can describe it as a trapdoor space, right? And that one you can describe as the challenge space. And how the simulation now works is as follows. Like how can we simulate signatures now? So the idea is, okay, when we get a signing query on message ME, what we do, okay, we look, did we embed it, did we use the challenge space, or did we choose this trapdoor space for that message? Okay, when we chose the challenge space, what we do is for signing, we just choose the honest key, PK1, right? And then we can simulate as that, like just honest signing, because we know the secret key in that case. However, if we embedded this message into the trapdoor space, right? Then we choose the unknown key. Why does that work? Okay, because we know the trapdoor, we can simulate signatures as that, like a trapdoor signing kind of. And now for the forgery, what we hope is, okay, for the forgery, we hope that the adversary, for the forgery, we hope that first we chose this challenge space for the forgery, right? And on the other hand, we also hope that the adversary chooses this challenge key, right, to give a forgery. And what that then says, what that gives us is essentially just directly a CDH solution. And the probability that the adversary chooses this space or that the message lies in this space is 1/2. And the probability that the adversary chooses this key to forge is also 1/2. So what we get with this was probability 1/4. We can get this, we can extract the CDH solution from the forgery. And all of that is tight, right? Because we didn't need to guess anything. Yeah, with that, I would like to conclude and add to your question.
Thank you. Questions?
Thank you for your talk. So I was wondering whether your techniques can also be applied on aggregatable signature, which is a more generic variant of BLS multi-signature, where parties sign different messages, not just one message.
I guess so. I don't know. I mean, how does it use? You have n signers, and each one
Yeah, they have their own sign
Yeah,
key.
and what about the security experiment? What does that, I mean, what's the security model? It's unforgeability. What does it say? When is the forgery successful?
So the parties sign different messages and then they combine it together. And then the verifier can actually verify the aggregatable message. I mean, the different signers sign different messages using their own signing keys, and then they aggregate their message into one aggregatable, for example, signature. And
Yeah, I guess it should work. I mean, each signer has just two keys, and then for each message, you can choose either this one or this. And then for the forgery, you hope that he chose the challenge key. I guess it should work.
Thanks. Any more questions?
Hey, thank you. Very interesting. Can you explain again, when you say choose, do you mean just randomly with a 50-50 probability, or you say, okay, they can choose whatever strategy to when use the PK0 or PK1?
I mean, usually you would just choose a pseudo-random, right? Like you have a pseudo-random function, and then for each message, you get a bit, 0 or 1. And then when the output is, I mean, the bit indicates which key you choose, okay? Which is essentially deterministic, right? But for the security proof, we don't do that, right? What we instead do, because for the challenge, like for the hash queries, we randomly choose one of them, right? Where we embed the challenge, okay? And then for the signing, for the key, we use the different one. And that's still to the adversary, it still appears like randomly. And so that's the idea.
Okay, I see. Thank you.
Thank you. Any more questions?
It sounded like you showed tighter security for just regular BLS signatures.
Yeah,
which
I mean,
also implies tighter security for multi-signatures. But first of all, you have tight security for standard signatures. Or
yeah.
Is that not the case?
Yeah, so we construct a single signer scheme, right? Which is tightly secure based on CDH and random multi-model. And then we extend it to the multi-signer setting, and that is not trivial, right? So we use this technique of proof of possession, but it does not, it does not immediately work. So we had to make some adaptations to make this work, right? But this reduction is also tightly secure. I mean, this one is tightly, this transformation. So in the end, we get tightly secure multi-BLS.
Thank you. Any more questions? Okay, if not, let's thank the speaker again. And let's thank all the speakers of this